This next presentation is called Structural Monitoring of a Breakwater using Unmanned Aerial Vehicles and Photogrammetry. And I'll start by introducing the motivation behind the work which was developed. So breakwaters can suffer erosion over time and undergo shape changes, which can be detrimental to the function of the breakwater. And the shape of a breakwater and the displacement of breakwater elements need to be monitored for maintenance and rehabilitation purposes, making sure the geometry is kept under acceptable parameters. And so the work being presented here is based on the 3D mapping of a breakwater using photogrammetry, using images acquired using an unmanned aerial vehicle, also commonly known as a drone. And in the end, we should be able to compare shapes acquired at different points in time and detect changes between them. The operations which were undertaken consisted of 3 steps. First, we programmed and executed 2 flights with the UAV at the port of Leixões in the city of Matosinhos in Portugal, acquiring images of one of its breakwaters which has a length of about 700 meters. And these 2 flights took place 3 months after one another. Then the images obtained were processed using photogrammetry software, resulting in 3D point clouds. And finally, we took meaningful results from the point clouds, being able to inspect the 3D geometry of the breakwater for any single one of the flights, and compare the point clouds from both flights. And now we'll go over the necessary equipment, both in terms of the physical components used for flights and in terms of the software used for the processing. So for the flights, we used DJI 600 Pro, equipped with a Ronin MX gimbal carrying the camera, which was a Phase 1 IXM50. And here are some of the component specifications. The ones that we found were especially critical for our operations were the drone's resistance to wind speeds, as well as its flight autonomy, which conditioned whether we could fly and for how long we could fly continuously, as well as the camera's resolution, which is quite high, and on the one hand it gives us a very high quality on the point clouds we obtain in the end, but on the other hand it limits the number of images we can save on each flight, and it makes the processing time higher. And as for the software, we used UGCS to plan automated flight missions. We used Pix4Z Mapper for photogrammetry, and then for point cloud processing and visualization we used Cloud Compare, as well as some Python code which we wrote ourselves. So, as I've mentioned, there were 2 flights which had some slight differences. On the first flight, the UAV covered the length of the breakwater twice, once in each direction, taking images from 2 distinct perspectives with the camera pointed in the direction of the flight, which you can see in the 2 examples below. And on the second flight, an extra run across the length of the breakwater was added, with the drone further out into the sea and the camera pointed towards the breakwater. This was an attempt at covering an additional angle that would capture some of the spaces between the tetrapods, which were obstructed in the other 2 views. After we acquired the images on our flights, we used them as inputs for the photogrammetry software. And it starts by identifying instances of the same feature across several images, finding matching points, which it uses to compute the locations of those points in the real world, together with the locations where the camera was when it took each frame. As for the outputs, the most important one in the context of this project is the point cloud resulting from each acquisition. You can see the full point cloud here on the left, as well as a close-up on the right. The first flight resulted in a point cloud with 170 million points, and the second one resulted in a point cloud with 270 million points. And even though the length of the breakwater which is captured is slightly higher, this still corresponds to a much denser cloud in terms of number of points. So we can conclude that the additional perspective we decided to include does have a significant impact on the point cloud's quality. And there are some other outputs we can take from the photogrammetry software, which include a triangular mesh, which represents our point cloud as a 3D surface, and a georeferenced orthomosaic, which shows us the breakwater as it would be seen from above. And now, having the point cloud, we can now inspect the geometry of the breakwater in various ways. For instance, we can navigate the point cloud interactively to visualize any region we want, and one particular characteristic of point clouds obtained with photogrammetry is that they retain the color from the image, which makes the visualization very clear. And we can also check the positions of points of interest or measure distances between them. And finally, we can extract profiles along the transverse direction to assess the shape and the slope of the breakwater surface and check it against the expected or required shape. And finally, we developed a methodology to check for changes in shape. So for this purpose, we compare the point clouds from the 2 flights we made, and the objective was to identify specific changes occurring in the 3 months between the 2 flights. And the steps of this procedure were extracting the same small section, about 50 meters in length, from each point cloud. This is because the comparison is computationally very intensive, so we have to break it into smaller parts, and then aligning the resulting point clouds, computing the distance between the point clouds, and visually identifying areas where this distance is high. And so, going into some more detail now, we extracted these 50-meter sections from each point cloud, and in order to align them into a common coordinate system, we picked some common points between them manually. They will already be roughly aligned to start with, due to the GPS position being recorded for each image, but the alignment won't be perfect, and so it can be improved, and that's why we did this. And at this stage we can detect changes in the point cloud geometry. We can compute the cloud-to-cloud distance on Cloud Compare, that is, how far each point on one of the clouds is to the other cloud. And then, after filtering large values, we get the following color map. And now, with this map, we're ready to identify changes. The highlighted areas of the map appear on the point cloud limits, especially near the water, whose representation on the point cloud is a little erratic, apart from the differences due to tides. But these highlighted areas also appear in areas in the middle of the point cloud. So if we inspect this highlighted area, we can check what it looks like on each of the point clouds. And after some visual inspection, it can be seen that some changes took place. Of course, at first sight, it's not very obvious what happened between them. But if we label different parts after a close inspection, it can be seen more clearly. So on these images, A, B, C, and D have remained at the same location after 3 months, but the elements marked with an asterisk have had changes in configuration. One of them seems to have moved to a different location within the same area, and the other one is no longer visible here. To confirm this, we were able to look back at the images from the flight and identify this area of the breakwater. And the perspective is slightly different, but we can see the exact same elements that we labeled in the point cloud, which confirms that this change really did happen. And now, to conclude, we have successfully automated a drone flight for image acquisition of a breakwater, which resulted in a high-quality point cloud generated using photogrammetry software, and we were able to detect changes in geometry that occurred over time through point cloud analysis. And this concludes the topic. Thank you very much.